Have you ever noticed how some devices, like a radio, can precisely tune into a single signal amidst many others? This precision in electrical circuits is often described by the powerful interplay between resonant frequency, Q factor, and bandwidth. At its heart, the Q factor and bandwidth are intrinsically linked to a circuit's resonant frequency. For any resonant circuit, the Q factor, which stands for quality factor, and the bandwidth exhibit an inverse relationship. This means that if one increases, the other tends to decrease, assuming the resonant frequency remains constant. Together, they define how sharply or broadly a circuit responds to a specific frequency. The core mechanism lies in how energy is stored versus dissipated within a resonant circuit. Resonant frequency is the specific frequency at which a circuit, often composed of inductors, capacitors, and resistors, exhibits its maximum response, like peak voltage or current. Bandwidth is the range of frequencies around this resonance where the circuit's response is still significantly strong, typically defined as the points where the power drops to half of its maximum. The Q factor then quantifies the sharpness of this resonance. It is literally the ratio of the resonant frequency to the bandwidth. A higher Q factor indicates a narrower bandwidth and a more selective circuit, while a lower Q factor means a wider bandwidth and a less selective response. Understanding this relationship allows you to predict how a circuit will behave. If you need a circuit that sharply selects a very specific frequency, like in a high-fidelity filter, you would design for a high Q factor, which inherently results in a narrow bandwidth. Conversely, for applications requiring a broader range of frequencies to pass through, such as in certain communication channels, a lower Q factor and wider bandwidth would be necessary. This principle is fundamental in designing oscillators, filters, and antenna matching networks. A fascinating insight is that the Q factor is not just a mathematical ratio, but a direct measure of a circuit's energy efficiency at resonance. Specifically, it represents 2 pi times the ratio of the energy stored to the energy dissipated per cycle. This highlights why high Q factor circuits are often sought after in applications where energy loss is critical, such as in radio frequency identification, or RFID systems, or highly sensitive measurement equipment. Additionally, the Q factor can be significantly affected by the equivalent series resistance of components, particularly inductors, making component selection crucial in real-world designs. Ultimately, grasping the symbiotic relationship between resonant frequency, Q factor, and bandwidth empowers you to precisely tailor circuits for specific frequency responses. It allows you to design systems that are either highly selective, zeroing in on a single frequency, or broadly responsive, accommodating a wider spectrum of signals. This foundational understanding is key to unlocking advanced circuit design and analysis.